I'd like to thank Brilliant for sponsoring today's video.
Today we're going to look at a really interesting family of natural numbers known as co-balancing numbers. And these numbers were introduced by G. Panda and P. Ray. And they have a pretty nice paper on the subject, which I'll link in the description. So longtime viewers of this channel may remember a video I did on balancing numbers. So these numbers are pretty similar, but I think this is interesting enough that we would tackle this type of subject again. All right, let's jump into the definition. So we say that a natural number n is a co-balancing number with co-balancer r if the sum 1 plus 2 plus 3 all the way up to n is the same thing as the sum n plus 1 plus n plus 2 all the way up to n plus r. So notice here we're summing the first n natural numbers over on the left-hand side, and on the right hand we're summing the next r natural numbers. So why would we have the word balancing in here? Well, we can think about this as being like a scale, so the equal sign is like balanced here. So let's look at our first couple of examples. So the first example that I haven't written here is 0, and in this case we do take 0 to be a co-balancing number. Then the first non-trivial example would be the number 2, and its co-balancer is 1. And that's because we have 1 plus 2 is equal to 3. So that's pretty obvious. The next co-balancing number is 14, and its co-balancer is 6. That's because if we add 1 plus 2 plus 3 plus 4 all the way up to 14, we get the number 105. But 105 is the same thing as 15 plus 16 plus 17 all the way up to 20. Then the next co-balancing number is 84, and its co-balancer is 35. And that's because if we sum 1 up to 84, we get the number 3,750, and that is equal to the sum from 85 to 119. Okay, so our real goal for this video will to get a closed formula for the co-balancing numbers. But in order to do that, we have a couple of things to do along the way, and we'll start with a little bit of exploration. So let's start with our defining condition for co-balancing numbers. And that is that we have the sum 1 plus 2 plus 3 plus 4 all the way up to n minus 1 plus n is the same thing as n plus 1 plus n plus 2 plus all the way up to n plus r minus 1, and finally n plus r. So I went ahead and put a couple of extra terms in here just to fill in the middle so that we could see more structure as we do this calculation or this exploration. And now I'll take this exact same equation and I will add it to itself, but the trick here is to reverse the order of addition on both sides. So let's do that. That means over here we'll start with n plus n minus 1. The next number would be n minus 2, and then we'll end with 2 plus 1. So that's exactly the same as what we have above. It's just that we've switched the order, obviously. Then we'll do the same thing over here. So we'll start with n plus r, the next thing will be n plus r minus 1, and then we end down here with n plus 2 plus n plus 1. And now we'll sum kind of across these columns. So let's do 1 plus n, notice that gives me n plus 1. Now we'll do 2 plus n minus 1, that also gives me n plus 1, plus this last term also gives me n plus 1. So the important thing here is if we add down all of these columns, we always get n plus 1. And in fact, it's quite easy to count up how many n plus 1s we have, given that there are n columns. So that means we're adding n plus 1 to itself n times. Okay, so that's cool. Now let's do the same kind of operation over here on the right-hand side of the equation. So adding down this column will give us 2n plus r plus 1. So we've got n plus n and then r plus 1. Then notice we get the same thing here. So we'll have 2n plus r plus 1 for slightly different reasons. That's because 2 minus 1 is 1. And then finally, down here at the very end, we have the same thing, 2n plus r plus 1. Okay, nice. But now the question is, how many of these do we have? And we don't have n of them like we did over on the left-hand side of the equation. We have exactly r of them. And it's pretty easy to count up the number of columns there and see that there are exactly r columns. So that means we're adding 2n plus r plus 1 to itself r times. So now, using the fact that multiplication is just repeated addition, that gives us a nice equation of n times n plus 1 equals r times 2n plus r plus 1. And now expanding out both sides of this equation will give us n squared plus n equals 2nr plus r squared plus r. Okay, but notice that we could view this as a quadratic equation where r is the variable and n is a fixed constant, where we have assumed that n is a co-balancing number. Okay, so in order to take advantage of that view and then solve for r, perhaps we would like to rewrite this a little bit so it looks like a quadratic equation in r. We can do that as follows. So we'll have r squared plus 2n plus 1 times r. So that comes from factoring a 2n and a 1 out of those two terms. So that comes from the yellow underline. And then this blue underline will be moved over to the other side of the equation, leaving us with minus n squared plus n equals 0. Okay, where I kept those grouped just for simplicity. And now from here we can apply the quadratic formula, and that'll leave us with r equals, so it'll be negative 2n minus 1, and then plus or minus the square root of stuff. But in this case we only need the positive square root, given that r has to be a positive number, and otherwise we would get a negative number. So that'll be plus, we have b squared minus 4 times a times c. I won't do the calculation out, but we'll end up with 8n squared plus 8n plus 1. And then this is, of course, all over 2. So like I said, that gives us a formula for our co-balancer in terms of our co-balancing number. But let's notice that it also gives us quite a bit more information. And that more information is that it tells us that n is a co-balancing number only when the stuff inside the square root here is a perfect square, because that's the only way we would ever get a natural number for r. So let's summarize that over here. So let's note that since n is co-balancing, that tells us that r must be a natural number. But if r is a natural number, that means that the square root of 8n squared plus 8n plus 1 is also a natural number. But if that's a natural number, that is exactly kind of the definition for 8n squared plus 8n plus 1 is a perfect square. So that gives us this nice condition that n is co-balancing, really if and only if 8n squared plus 8n plus 1 is a perfect square. So that's a pretty nice condition to start with. And in fact, you can check that it works with our first few examples over here. So if you plug n into this expression 8n squared plus 8n plus 1, you'll end up with 49. But 49 is a perfect square. So let's put that into contrast with what you get if you plug 3, which is not a co-balancing number, into that quadratic expression. And that would give you 97, but 97 is not a perfect square. So that's just an example of how this can quickly test whether or not we have a co-balancing number. Okay, so next let's look at a theorem which will allow us to build all co-balancing numbers.
Now I'd like to take just a moment to talk about today's wonderful video sponsor, Brilliant.org. Brilliant is an online interactive learning platform with thousands of lessons on a variety of topics ranging from simple to advanced. And in fact, there's new material added every month. So that means you'll always have something new to learn. Brilliant offers a multitude of courses in all STEM fields. Whether your thing is math, science, or computer science, Brilliant has a course for you. Brilliant's interactive and unique take on learning with awesome hands-on puzzles and graphics will have you mastering skills in no time. I was really happy to find Brilliant's course on solar energy. It gave me a basic understanding of what's happening in all of the components that I installed in my RV. So what are you waiting for? To get started for free, visit brilliant.org/Michael Penn or click on the link in the description. And the first 200 of you will get 20% off Brilliant's annual premium subscription. And one more time, I'd like to thank Brilliant for sponsoring today's video.
So we just finished developing the intuition and a bit of a sketch of a proof for this proposition. And that says that n is a co-balancing number if and only if 8n squared plus 8n plus 1 is a perfect square. And now we're going to look at the following theorem, which will indeed help us generate all co-balancing numbers, as we'll see just after proving it. And it says that if we define a function f to be 3x plus 1 plus the square root of 8x squared plus 8x plus 1, then if n is a co-balancing number, so is f of n. So that means all you have to do to make a new co-balancing number is apply this function f again. Okay, so let's maybe see how this proof goes. So let's start with the hypothesis. So let's suppose that n is a co-balancing number. But then by our proposition over here, that tells us that 8n squared plus 8n plus 1 is a perfect square. So let's write that down. So that means, like I said, 8n squared plus 8n plus 1 is a perfect square. Okay, but that means that when we evaluate f at this special n, we get 3n plus 1 plus the square root of 8n squared plus 8n plus 1, which is itself a natural number. So in other words, to put this all together, we have m, which is equal to f of n, is a natural number. Now we haven't yet shown that it's a co-balancing number, but it's at least a natural number, not some crazy irrational number. Okay, now let's set up an equation and solve for n in terms of m. And this is the equation that we'll set up right here. So we'll have m equals 3n plus 1 plus the square root of all of that stuff. Now let's start to move some stuff around. So this is going to give us m minus 3n minus 1 squared equals 8n squared plus 8n plus 1. So I just subtracted the 3n plus 1 to either side, to the other side of the equation, and then I squared both sides. But then expanding out this left-hand side will give us the following object. So we'll have 9n squared plus 6n plus 1. And then plus m squared, and then minus 2m, and then minus 6mn. So like I said, that's from expanding out this left-hand side. I'll let you guys check that, but really it's just a bunch of symbolic manipulation. There's nothing fancy going on there. And then we set this equal to 8n squared plus 8n plus 1. And notice we can start simplifying a little bit. So notice this 1 over here on the left will cancel this 1 over here on the right. And then next, this 8n squared on the left will cancel this 9n squared down to just n squared. And then this 8n over here will cancel this 6n down to negative 2n. Then we can start putting things together. So notice we'll have n squared minus, let's see, 2 plus 6m times n. So that's collecting all of the n terms, the terms that are linear in n. And then we'll have plus m squared minus 2m equals 0. And now we can view this as a quadratic equation where n is a variable. And that'll allow us to solve for n. And what we'll end up with is something that's quite familiar. And that will be n is equal to 3m plus 1 1 minus the square root of 8m squared plus 8m plus 1. So I won't go through all those details. Like I said, that's just applying the quadratic formula. But let's recall that since n is a co-balancing number, that means it's a natural number. So we have this thing is a natural number. But if this whole expression is a natural number, that means the square root is a natural number. But if the square root is a natural number, that means this thing that I've boxed in yellow is a perfect square. But if that thing that I've boxed in yellow is a perfect square, that means exactly what we want, and that is that m is co-balancing. But check it out. If m is co-balancing, then f of n is co-balancing just based off the definition of m, but that's exactly what we wanted to prove for this theorem. Okay, so now we're going to present a fact which is built off this theorem, but we won't prove it. So we just finished proving that if n is a co-balancing number, so is f of n, where f of n is 3n plus 1 plus the square root of 8n squared plus 8n plus 1. So let's check that. So if we start with our co-balancing number 2 and we apply f, notice we will get 3 times 2 plus 1, that's 7, and then plus the square root of 49. That's what that expression simplifies to if we set n equal to 2. But 7 plus 7 is 14, so we're good to go there. 14 is the next co-balancing number, and we saw that as an example before. Then, if we apply f again, we'll get the number 84. And if you recall, 84 was the next example of a co-balancing number that we had before. So we can apply f again, and we'll get 492. That's the co-balancing number after 84. Then, I'd like to point out that f inverse will take us in the reverse direction. So f inverse will take us from 492 to 84. It'll take us from 84 to 14, and then it'll finally take us from 14 back to 2. And also f inverse has that format that we saw before, which was 3x plus 1 minus the square root of 8x squared plus 8x plus 1. We actually calculated f inverse along the way. Now I've got the following fact which is super important, and that is that there are no co-balancing numbers between n and f of n, and we won't prove this. But what does this mean? Well, there are a bunch of numbers between 2 and 14, but by this fact, none of them are co-balancing numbers. Furthermore, there are lots of numbers between 14 and 84, but none of them are co-balancing numbers. There are lots of numbers between 84 and 49, but again, none of them are co-balancing numbers. So this allows us to generate all of the co-balancing numbers. Okay, so now let's work from here to a nice recursion on the co-balancing numbers. And in order to do that, we'll introduce some notation. So let's say Bn is the nth co-balancing number. And then furthermore, let's set b of 0 equal to 0, and then b of 1 will be equal to 2. Great. And then we'll notice that bn minus 1 is equal to f inverse evaluated at b sub n. But we can rewrite this as 3b sub n plus 1 minus the square root of 8b sub n squared plus 8b sub n plus 1, based off of the behavior of f inverse. Furthermore, we know the next one, bn plus 1, equals f evaluated at bn, which is 3bn plus 1 plus the square root of 8bn squared plus 8bn plus 1. But the fact that we've got a positive square root here and a negative square root above motivates us to add these two equations together. And let's see what that'll leave us with. We'll have bn plus 1 plus bn minus 1 equals 6bn plus 2, and those square roots cancel. Then, the great thing about this is we can easily solve for bn plus 1, and we'll have a recursion. And so that gives us bn plus 1 equals 6bn minus bn minus 1 plus 2. So we've got this nice two-step recursion for our co-balancing numbers. Okay, so now let's do a linear algebra trick to get our closed form. So on the last board, we developed the following recursion for our cobalancing numbers. So if b sub n was the nth cobalancing number, then b sub n plus 1 was equal to 6bn minus bn minus 1 plus 2. b0 was 0 and b1 was 2. Those were like the seeds for our sequence. But this plus 2 makes this thing a little bit hard to work with. So instead, what we'll do is we will turn this into a homogeneous recursion with a little bit of substitution. And that substitution will be to set Cn equal to Bn plus 1/2. But that means that Bn is equal to Cn minus 1/2. Then I'll let you guys work out the very simple details, but that provides us a new recursion, which is a little bit easier to work with. So we'll have Cn plus 1 is equal to 6 Cn minus 1. And then we will furthermore have C0 equals 1/2 and C1 is equal to 5/2. Okay, so I've got my recursion up here. I moved it up. I also added like a trivial version of it above. So we've got Cn is 0 times Cn minus 1 plus Cn. Now what we can do is rewrite this as a vector matrix equation. So we'll have the vector Cn plus 1 is the same thing as the matrix 0, 1, -1, 6 multiplied into the vector Cn minus 1 times, or Cn minus 1 Cn. Okay, but in fact what we can do is extend this all the way back. So let's rewrite one more step of this. So we have 0, 1, -1, 6 squared times Cn minus 2 times Cn minus 1. And that's just applying the recursion one more time. But like I said, we can take this all the way down to the ground and we'll get that this is 0, 1, -1, 6 to the nth power times the vector C0, C1, but that's the vector 1/2, 5/2. So something like that. And this is a really good place to be, but before we make our next step, I want to put it all back in terms of b sub n. So after moving some things around on the last board, and then based off of our change of variables, we have the following formula for our b sub n's, but we can do a little bit better. We have this vector b sub n plus 1 is the nth power of our matrix 0, 1, -1, 6, 1/2, 5/2, and then we're going to subtract 1/2 times the vector 1, 1. And now the big trick here will be to take this nth power of this crazy matrix and then expand it into a diagonal matrix being conjugated by an invertible matrix. And I won't go through all the details here. I've done this a couple of other times on the channel. You guys can check that out if you wanted to. There should be a link up in the card if you'd like to. But this matrix factors as follows. So we end up with the following kind of behemoth of a factorization. So we've got this crazy matrix over here on the left that involves this 3 minus 2 root 2 and this 3 plus root 2. We've got another crazy matrix on the right. So this matrix on the left is the matrix of eigenvectors for our original matrix. And 1/8 times the matrix on the right is the inverse of that matrix. So in fact, we're conjugating this diagonal matrix by these two invertible matrices in order to make this diagonalization procedure. And then this nth power showed up as the nth power of the diagonal entries of our final matrix. So we've got 3 plus 2 root 2 to the n and 3 minus 2 root 2 to the n in the end. But the great thing about this is we can easily expand all of this out just using matrix vector arithmetic to get a closed form for Bn. And there's not a lot interesting going on with the development of this closed form. So that being said, let's just get the result on the board. So there it is. We've got our closed form for our nth cobalancing number is 1 plus the square root of 2 to the 2n minus 1 minus 1 minus the square root of 2 to the 2n minus 1 all over 4 times the square root of 2. And then we have to subtract by 1/2. So there's actually an interesting step which I left out where you have to denest a square root. And that shows up when you multiply this whole thing out. So maybe post in the comments which square root you have to denest to get exactly these two guys right here. And like I said, I've done a problem where we find the closed form for a recursively defined sequence using this linear algebra technique. That should be on the screen right now if you'd like to check out the details. And that's a good place to stop.